In this presentation, I will share with you another method that can be utilized to find a relationship among variables. Simple regression, and more specifically, linear regression, is a method used based on correlation that allows the prediction of one variable from another. The greater the strength of the association, the better the prediction. It means that one would not go on to conduct a linear regression unless the two variables that are being examined have shown some correlation. In predicting the dependent variable based on the independent variable, we follow what is known as a probabilistic model. In this model, you will be familiar with y equal beta naught plus beta 1x plus an error factor. This is the same as if we were solving for the slope of a line, and you are perhaps more accustomed to y equal mx plus c. In essence, it represents the same formula. Y here is the dependent or the response variable, the one that is being predicted. X is the independent variable or the predictor variable. And so we are using the variable x to predict what will happen to y given a change in variable x. Our error factor is usually what is considered the deterministic component, and when we use software like SPSS, what it produces for us is a standard error of the beta coefficient that it will calculate. In this formula, beta naught is the y-intercept of the line, which means it is the point at which the line intercepts or cuts through the y-axis. It can also be explained as the point at which x is equal to 0. Beta 1, on the other hand, is the slope of the line, that is, the change or the amount of increase or decrease that is seen in component y given there is a change or an increase in the variable x. So if we use this graph to demonstrate what is happening, we are suggesting that from a correlation, there is going to be an increase in x given an increase in y, which would be a positive correlation. However, we would like to know the unit of change that is taking place as y increases and the effect that x is having on y. And that is known as the slope of the line. And you can see here in this graph, we are calculating beta 1 to be the slope of the line. And essentially, all we're doing is solving for this equation of the line. So a positive slope will imply an increase in y by the amount of our slope, which is beta 1, for each unit increase in our x-axis, which is also our independent variable. A negative slope, on the other hand, would imply that y, which is our outcome variable, decreases by the amount of beta 1, again, still the slope of the line. While it is important for you to understand the concept behind the linear regression, it is more important for you to understand the broad concepts as to why we do a linear regression. We do a linear regression because mainly we're trying to predict our y variable or our dependent variable on the basis that x have some influence, which is our independent variable, have some influence on this dependent variable. In the equation that we looked on when we discussed the correlation analysis, we were examining the effect of age and weight, with age being the independent variable and weight being the dependent variable. From that correlation, we found that there is a strong positive correlation, meaning as age increases, weight also increases. If we wanted to find out by how much weight increase with every 1 year increase in age, we would do a simple linear regression. Let's take this example. Here we have, again, as was explained, age and weight. We have 6 participants and their age ranges from 5 through to 9. Their weight ranges from 8 through to 13. We have calculated a correlation coefficient R, which is 0.759. And those of you who did the self-practice or the learning self-check, you would realize that this number is familiar, this 0.759. And that is the correlation. So on the basis of this correlation, we will move on to do our simple linear regression. From that, we can identify that a model is given. Here in this model, we have beta naught. Again, remember what beta naught is. Beta naught is a constant, and we are saying that this is the point of intercept. X intercepts y. And this is 4.692, represented here as a constant. Then we have our slope of the line, which is our beta 1 of x. And this is what we're saying. This is the change that is occurring in weight as age increases. The other important aspect of this output from SPSS that is important is the significance value. This significance value of 0.08 is what we are comparing to the alpha. And remember, our alpha is 0.05. And the rule applies just the same, that if our significance level or p-value is less than alpha, then we have a significant, statistically significant test. However, as you can see, 0.08 is greater than our alpha of 0.05, which means that this is not a statistically meaningful result. So how do we interpret this output? It is important to understand that what this is saying is that with every 1 unit or every 1 year increase in age, weight increases by 0.923 kilograms, which is represented here, the slope of the line. So how do we go ahead and formulate a conclusion from the regression analysis output that we get from SPSS? Your conclusion could sound something like this. While weight increases with age, the relationship is not statistically significant. Beta is equal to 0.923 and P is equal to 0.080. And our beta here is suggesting our slope, and our p-value is what we get from our output over here.